Put down quantum numbers. Basically we have 4 types. We have, so let's say quantum numbers and application, because if I just say quantum numbers it looks as if it's, so the first one is principal. Principal quantum number has a symbol of n. It has a symbol of n. The next one is Azimuthal, which is also called subsidiary, has a symbol of L. The third one we have magnetic quantum number, which has a symbol of ML. We have the fourth one, spin. Now we're going to be explaining the function of each of them, and after explanation I'm going to actually tell us the various ways questions can be asked pertaining to this. Now, what is principal quantum number? Please put down. Now, principal quantum number is the quantum number that describes the shell or energy level of an atom. Now, look at this. Every atom is presumed to have something like a nucleus at the center and then a shell, coming out. In secondary school, we know this as the shells we know in secondary schools were the K, L, M, M and N shells. Now these shells are basically what you're seeing here. Now let's see an atom like a spherical substance like what we have here. This thick dense center is what we call the nucleus, which was discovered by Rutherford through the gold foiled experiment. So this is the nucleus here, and around this nucleus there is a shell. The first shell is a K shell, the second shell is a L, and the third one is the M. Now, but principal decided to tell us that instead of us to use letters to actually designate each of these, principal now said this shell is something as saying energy level. So if an atom should have 4 shells, you can equally say that atom has 4 energy level. In place of K, this is the first energy level. You don't count it from outward. You count it from what? Inside. So this is the first shell. Shell number what? 1. This is a what? 2, and this is a what? So whenever we talk about shells, this is basically what we are referring to. And which quantum number describes the shell of an atom is what? Principal. In secondary school, they use K, L, M, and N to designate shells, right? So another way to designate shell is that shell K is shell number 1. Shell L is shell number what? Shell M is shell number what? And this is shell number what? So just in case somebody asks you which quantum number describes the shell of an atom, it is the what? Please, shell and energy level are what? The same. They are the same thing. Do you understand? And another thing I would like to tell us is that if you noticed, the shell numbers are whole integers. They are what? There's nothing like 1.5. Shell does not have any 0 shell. The first shell starts from shell number 1. The second one is shell number 2. There's nothing like 1.5. So principal quantum numbers always start from n, which is a principal quantum number, right? Start from 1, 2 to all positive integers. So therefore, you can never see a principal quantum number having 1.5. So in case of exam, somebody asks you, can we have 1.5 shell? It's not possible. Shell is always a whole what? Number. Do you understand? Either you have shell 1 or shell 2 or shell what? 3. So the values for principal always start from 1 for the first shell, which is the K shell, L, which is the what? 2, which is the L shell, M, and so on and so forth, right? So that is that for principal quantum number. Let's look at the next one, azimuthal or subsidiary. Azimuthal or subsidiary quantum number. Please put down. This quantum number describes the shape of orbitals. It describes the shape of orbital, number 1. The next one, it tells the types of orbitals present in a shell. It tells the types of orbitals present in a shell. It varies from 0 to n-1. Its values always start from 0 and stop at n-1. I will explain that. And most importantly, note, it is dependent on principal quantum number. Dependent on principal quantum number. It is dependent on principal quantum number. What do I mean when they say something is dependent? It simply means that the value of this guy, the value of azimuthal, we said it starts from 0 and ends at what? n-1. That means if there is no n, right, there won't be any L, because n is involved in its formula. For me to get the value of L, I need what? N. Now let me explain something. Every shell is more like a house, a room. Rooms normally have beds, right? Now beds are what we refer to as the orbitals, right? Orbitals are regions in an atom where electron resides. For example, in the case of classrooms, right, the chairs are the orbitals, because if a student should enter the classroom, you sit down, right? So but inside bedroom, the bed is where you cannot enter a room and see somebody just standing, right? It's either the person is lying down or is sitting on the bed, right? If you go to parlor, where you're likely to see human beings are on the couch. So in atoms, the space where electron always reside is what we call the what? Orbitals, right? So how do we know the number of orbitals that is present in a shell? It is the work of what? Azimuthal, right? For example, you enter inside a bedroom. How do you tell that this room is going to have 5 beds, right? That is the work of this azimuthal. Now let me tell you something. I believe before now you've seen something like 3s, 3p, and 3d, right? In electronic configuration. You've seen 2s and what? 2p. Now if you noticed, both of them, they have 2, 2, right? These 2 means their s and p are on the second shell. These numbers you're seeing here are the shell. Let's say shell 1, shell 2. This shell 2 has s, and this shell 2 also have what? P. How do we know? It is the work of what? Azimuthal, right? So let's now class look up. Now we have azimuthal quantum number. Now designation / orbitals. Now what we want to do here is azimuthal says if I have a value of 0, note that this value of 0 is for s orbital. Remember we said azimuthal, so in place of this I'm going to put numbers, right? Now this guy is now what is translating the numbers to the various orbitals. This stuff you're seeing is designation or what? Orbital. So if azimuthal has a value of 0, because azimuthal will always start from what? If azimuthal has a value of 0, that designates what? S what? Orbital. If this guy has a value of 1, that designates what? P. A value of 2, that designates what? A value of 3, that designates what? Now, these are the various designations for orbitals. So let's now see how we can use this to tell the number of orbitals that are present in a shell. Right? Let's say, for example, if I have, this is an atom. This is shell number 1. And this is what? Shell number 2. Right? Now, let's say for shell number 1, how do we designate shell number 1? We say principal equals to what? N. Because remember, principal is N, right? And principal, if N equals to 1, it means that we are referring to shell number what? 1. If N equals to 1, L says my value will always start from 0 and will stop at what? N minus 1. So come here, put 0. What is the N in this case? 1 minus 1. There will be nothing here since there is already 0 here. Right? Now, if N equals, for shell number 1, you can only have one azimuthal, which is 0. You can see that here, right? Now, what is the designation? Which orbital did azimuthal give to number 0? Look at that. S. So this is S. So shell number 1 can only have what? 1s. That is why you can never see 1p. If N equals to 2, this is shell number 2, right? Now, azimuthal says if N equals to 2, my value will always start from what? 0. And will stop at what? What is N in this case? 2, right? 2 minus 1 is what? 1. Now, once again, azimuthal used a letter or a value to designate each number, right? For 0, he said, which orbital is for 0? For 1, which orbital is for 1? So shell number 2 can have what? 2s and what? 2p. So with this now, azimuthal is now telling us that if I have shell number 2 can only have s and what? P. That is why you can never see 1 having 1p. Right? You can never see 2 having 2d. So if I come back here and I will say, if n is equals to 3, my L will be 0. It will start from 0, right? And will end at what? What is n here? Are you following? N here is 3, right? 3 minus 1 is what? 2. So this guy will start from 0 and end at what? What is the value between 0 and 2? Whole numbers. We are dealing with whole numbers, right? Is 1. So this is what? What? And what? So therefore, shell number 3 can have what? 3s, 3p, and what? So that is basically the number 2 function of azimuthal. I just explained. I've not explained this first one yet. So in case somebody asks you, which type of quantum number can we use to identify the types of orbitals? Right? It is azimuthal. But most times they will not use the word orbital. They use the word subshell. They use the word what? Class, look up. If you noticed, the shell here is what? 3. They have something in common here, 3, right? But here is S, here is P, and here is what? So that means 3S, 3P, and 3D, they are subshell. It's just like you and your siblings. All of you guys have the same surname, but the first name is not the same, right? So you guys are sub of your parents. Your parents are the main shells now, right? You guys are the subsidiary of the shell. That is why it is called what? Subsidiary quantity. Something that is coming, that is attached to somewhere, right? So 3s, 3p, and 3d are subshell of shell number what? 3. Do you understand the concept? So in other words, how can this question be asked? Azimuthal quantum number can be used to tell the type of orbitals present in a shell, or it can be used to tell the number of subshell. So tells the number of subshell Most times, this subshell, they may not really use subshell. They can also use sub what? Do you know why they use sub level? Remember, shell, another name for shell is energy level, right? So if they will not say sub energy level, it's too long. So that's why they just said what? Sub level. So these are the three. We have done this. We have done this. So Azimuthal tells us the types of orbitals. It also tells us the type of subshell or sublevel. Now let's look at the first function of Azimuthal before we... Alright, so we're talking about how to identify the shape of orbitals, or how we came to terms with the fact that orbitals have shape. Right? It was Azimuthal that helped us to do that. Now, in the previous illustration that I gave us, I said Azimuthal, let's say orbitals. Azimuthal of 0 is s orbital. Azimuthal of 1 is p orbital. Azimuthal of 2 is z orbital. Azimuthal of 3 is f orbital. Now, how can we really tell the shape of these orbitals? It's basically the work of Azimuthal. I wouldn't really want to spend so much time, since it's positiemi we are actually going for. I don't want to give us so much illustration. Now, s orbital is spherical or donut. This is dumbbell. So these are the shape of f orbital. Doesn't really have a shape like that. It's a bit complex. So this, we can call it donut. So this is what we have. So s orbital is spherical, p orbital is dumbbell, d orbital is double dumbbell. So just take note of that. Now I'm just trying to give us head up on how questions can be asked. Okay? Let's look at magnetic. We just completed principal and azimuthal. Now magnetic is the third form of quantum number. And the function of this guy, the first one is, it tells us the number of suborbitals present in an atom. Now this tells us the number of suborbitals. Azimuthal tells us the type of orbitals. Is it going to be s orbital? Is it going to be p? Is it going to be f, and the rest of them? Now this guy tells us the number of suborbitals. Number 2, it tells us which orbital is degenerate. Which orbital has degenerate orbitals? Now, how did we actually come to terms with this? Now, when an orbital is actually spined in a magnetic field, it gives rise to magnetic quantum number. Azimuthal gave rise to the orbitals. Azimuthal will tell us whether this guy is s orbital, p orbital, d orbital. Now when you pick up each of those orbitals and spin it in a magnetic field, it will actually tell us if this guy can give rise to further orbitals or not. So now, having done that, let's use this side for this magnetic first. Please put down. Note, magnetic, it varies from minus L to 0 to plus L. Do not forget that minus L, L is azimuthal. Don't forget that. So azimuthal is telling us the type of orbitals. And the next part, note, magnetic depends on azimuthal. Azimuthal depended on principal. Now magnetic is depending on azimuthal. So that is how it is. Now, out of the 4 quantum numbers, it's only azimuthal and magnetic that are dependent on another. Principal is independent. Spin is also independent. So take note of this. So what do I mean? If L equals to 0, which orbital is that? S orbital. Now ML says whatever L is, start from the negative of that to 0 and to the positive. But we cannot have minus 0, 0 and plus 0. 0 is 0. So once L equals to 0, ML must give us what? That is why S orbital only has 1 orbital. So if you're drawing box for S, you can only see something like this for S. But if you're drawing for P, you see 3. If you're drawing for D, you see 5. So S orbital has no what? Suborbitals. Now what if we have, if L equals to 1, which orbital is that? P orbital. Now ML will always start from minus of L, right? So this guy will start from minus of 1, right? Proceed to what? 0. So what? Plus 1. Right? How many numbers can you see here? 3. Each of these numbers stand for orbitals. So P has how many boxes here? 3 boxes. So therefore, P has how many suborbitals? 3 suborbitals. So we'll say P orbital has 3 suborbitals. Now, if L equals to 2, that is the orbital. ML will start from the negative of this to the positive. So we'll have minus 2, minus 1, 0, plus 1, and what? Plus 2. Now count these numbers. How many numbers can you see there? 5, right? So therefore, D orbital has 5. Now listen, there's what we call degenerate orbitals. This word here, degenerate simply means something that have the same energy, right? Now, any orbital that has suborbitals are considered to be degenerate. S orbital does not have any suborbitals, right? So S is not degenerate, right? But P, if somebody should ask you how many degenerate orbitals is present in P orbital, what's the answer? It's 3. Degenerate simply means that 3 of us will have the same energy because we are coming from the same source. This is P. 3 of them are under what? P. So 1, 2, 3 have same energy. The word degenerate means same energy. P orbital has 3 degenerate orbitals. D has how many? 5. What of F? If L equals to 3, that's ML will start from the negative of this. So have minus 3, how many boxes can you count? 7. 1, 2, 3, 4, 5, 6, 7. It means that F orbital has how many suborbitals? 7. How many degenerate orbitals is present in F? 7. So that is basically how this thing works. With what we have done now, Class, go back and check your past questions under quantum numbers. I don't think there's any question you see and you'll not be able to solve it. Let's look at spin quantum numbers. Now, spin quantum numbers is a type of quantum numbers that describes the orientation of the spin Remember I said an orbital is a region where electron resides. So for S orbital, S has just one orbital. P has 3. D has 5. Now look at this. Each of these boxes are orbitals. Each of them are orbitals. And each box can take maximum of 2 electrons. And those 2 electrons, their spin, they must be in opposite direction. You cannot have this like this. This is wrong. When electron is spinning up, then the next one should spin what? The first electron that enters the orbital has to go up. And the next one has to do what? Now, the value of spin for the first electron is always plus half. Spin always have a value of half. Is either plus or what? Minus. Plus is the one that enters first, the one that is pointing up. And minus is the one that is doing what? Pointing down. No 2 electrons, listen, in an orbital can have the same spin. You cannot have something like this. This is wrong. Right? You cannot have something like this. This is even wrong because the first electron that enters must do what? Point up. It's a must. I did not say it will. So the correct thing to do here is the first one that you're writing out should be what? Pointing up. The next one should be what? Pointing down. So take note of that. If you come here, this goes like this. This goes like this. This goes like this. So spin quantum number is a quantum number that describes the orientation of the spin. The one that is pointing up is always having a value of plus half. The one that is pointing down is always having a value of what? Minus half.